Okay, part 3. Starting with this problem, read your scenario and sketch your graphs. Okay, here are your answers. So this one kind of was an easy one. Went back to easy. Kai travels west while accelerating. So I didn't say where he started, so I just went ahead and started him at the origin. But if you didn't start him at the origin, it doesn't really matter as long as your line has an increasing negative slope to it. And an increasing negative slope gives us an increasing negative velocity. So if you're speeding up while going west, that's a negative acceleration. Or just the fact that it's a negative slope, it's a negative acceleration. Alright, next scenario. We're almost done, guys. Almost done. Here's your scenario. So read that, sketch, pause, come back for answers. Okay, Isabella travels east at a constant velocity. So here's my constant velocity. And then she speeds up for a short time, so now I have an increasing slope right here. And then she slams on her brakes, so a harshly decreasing slope, to a quick stop. Now it never slopes back down because she didn't go west. She never went west, she only went east. So the entire time her position should be increasing towards the east. Okay, so right here it's increasing towards the east at a constant rate. And then speeds up and then slows down. And then here we have a constant velocity followed by speeding up followed by slamming on the brakes. Here we have no acceleration followed by positive acceleration followed by a large negative acceleration. Okay, go to the next scenario. Hang on, Caleb. My son's calling me, so I gotta take this call. Okay. Yeah. Alright. Love you. Love you too. Bye. Okay. Next scenario. Alright, we have a ramp. And some of us did this in class and some of us didn't, so you may have seen this. We have a ramp. The ball rolls down the ramp. It's going to accelerate down the ramp because gravity's pulling on it. And then once it hits the floor, I'm saying there's no friction, so it's not going to roll to a stop. So it's going to continue on at a constant velocity because there's no friction to slow it down. So here we have an acceleration. Here there is no acceleration. And don't worry about the up and down, just think left to right. Okay, so as long as it's moving to the right, we're going to call that positive. It never moves to the left, so there's no negative velocity. Okay, don't think about up and down, just left and right. Okay, pause your video and really think about it. Come back for answers. Alright, so here's our answers. Let's hold this. Okay, so it's moving in the positive direction and it's increasing in speed. So it's going to have an increasing positive slope here. So it's kind of curved upward. Starts out slow, but it's moving to the right and it's speeding up. So there's a little curve there. And then it hits the floor, and at the floor it begins to go a constant velocity. So here its velocity at first starts from rest and it increases in the positive direction, but when it hits the floor, constant velocity. And then here we have a positive acceleration while it's speeding up, and then no acceleration. Okay, last scenario. Keep that PT-VT-AT graph and let me know what one addition you have to make to it if we add another slope. What's the one addition that we would need to make by adding this slope? Okay, back for answers. So here's what we would need to do. It's going at constant velocity, but as it goes up the ramp, it begins to slow down. So now its slope is going to have to still be positive because it's still moving to the right, but it's going to have to decrease. Okay, the slope will have to decrease. Its velocity slows to 0 while it's still moving to the right, so still not a negative velocity. And if it's moving to the right, which is positive, and slowing down, that's a negative. That makes a negative acceleration, right? Still moving to the right, but it's slowing down. A positive and a negative make a negative acceleration. Or constant negative slope, constant negative acceleration. Okay, that's all of the scenarios. And then just a little extra tidbit for the test coming up. I'll just go ahead and use this. You could have a position time graph or a velocity time graph, and it might have several lines on it, like this. And I might say, which one of those objects are moving at a constant velocity? And so it could be one or more answers. So if you have a constant slope on a velocity time graph, you have a constant velocity. I might say, which one of those objects are accelerating in the positive direction? And you would say, none. I might say, which one of those have no velocity at all? And you would say, A. Okay. Which one of those are slowing down while traveling in a negative direction? You would say B. Okay. So there's just some ideas to give to you. Here's some others that you might see on the velocity time graph if you get that particular version. Well, let's see here. I guess that's good. Okay, I might say, which one of those have a positive acceleration? Which one of those have a negative acceleration? Okay, so positive, positive slope. Negative, negative slope. I might say, which one of those are changing direction? Well, in this case, A was traveling, let's say west, and slowing down to 0, and then started traveling east and speeding up. So it traveled west and east, so A changed directions. B traveled east, slowing down, and then west, speeding up. So it also changed directions. Okay? So there may or there may not be lines on there that have changed directions. Same with the PT graph. So I'll ask you things like that. Which one has the greatest change in velocity? Well, that's pretty hard to tell between these two because they're very close to the same. Let's do another one. Maybe I have one that's like this. So the one that has the steepest slope would have the greatest change in velocity. I don't know. Whoops, I called that C. I can't have two C's. So just those are some examples. Do good, do great on that test. Make me proud.